Hey vSauce, Maxim here. When I drop these double pendulums, they move similarly at first, but soon diverge into random and chaotic motions. Surely this is all random. Or is it? Daniel Bernoulli was a Swiss mathematician in the 1700s, a pioneer in chaos theory. He found the system of double pendulums to be chaotic and seemingly random. It wasn't until
Jean le rond d'Alembert.
years after Bernoulli would discover and write down the differential equations needed to model such a system, because such a system can indeed be mathematically modeled. This motion, as wild and chaotic as it may seem, is indeed predictable. With a few simple equations, called the Lagrangians, we can model this. We define the kinematic constraints and calculate the kinetic and potential energy. Kinetic energy is based on how fast things move, and potential energy is based on how high they are. Together, these make up what's called the Lagrangian. With the Lagrangian, we use the Euler-Lagrange equation to get the equations of motion. After all the math, we end up with two differential equations. It's possible to predict the movement of this double pendulum, but that doesn't answer another question that we have.
If we drop the same pendulum from the same point at the same time, why do pendulums diverge at all? To answer this question, we built one of our own. After laser cutting, gluing, sanding, and borrowing ball bearings from the engineering room, we built one of our own. Getting a long exposure camera to measure the motion of the pendulum, we took some incredibly long exposure shots. We dropped from the same 90-degree angle 5 times. Surely they must be the same. Wait, that's not the same. But why? Double pendulums are extremely sensitive to initial conditions. Even a tiny little difference between two starting positions can lead to insanely different results after a few spins. We can't measure with infinite precision and infinite tolerance, which are both practically required to have a double pendulum spin in the same shape. Even then, external conditions could provide enough to throw off all of that infinite precision we had previously. Even a tiny little breeze, a tiny perturbation in the air that the double pendulum travels in can disrupt everything.
Double pendulums aren't random, but they are chaotic. This tiny difference, having huge impacts, is called the butterfly effect, and you're probably already familiar with it. A butterfly's wings flapping in Spain could lead to a hurricane in Florida. Tiny changes in the initial conditions can lead to extreme consequences, and nowhere is that modeled better and simpler than the double pendulum system. Why should we care? Because double pendulums can help us measure gravity, keep time, and even study earthquakes. The principles behind pendulums are still used today in seismographs, sensors in electronics, and metronomes for music. It may just look like a wobbly toy, but it shows us we can model complex systems for math.